Okay, thanks a lot. So yeah, it's a great pleasure to be here. Thanks to the organizers for inviting me. In my talk, I will basically start where Carsten left off. I'm going to talk about neutrinos as a window to new physics, but of course, sterile neutrinos and the short baseline anomalies will also play a role in that talk. More broadly speaking, let me start with those two plots. This is a plot that we've already seen earlier this week in Andre's talk. That's the famous unitarity triangle in the quark sector. And what's amazing here is how so many different measurements come together to constrain the location of the tip of this triangle to this very small dot here. And that's basically a measure of how well we understand quark mixing. Now we can make a similar plot in the neutrino sector. This is from the NewFit collaboration. That's what it looks like. You see that it doesn't come together in such a small region yet, but it's more on a circle. That's mostly because we don't have the value of delta CP yet. But the general idea here is the same, but you can see that we still have some way to go in the neutrino sector compared to the quark sector. And now, of course, it's great to see all of these measurements come together, but of course, it would be even greater if they did not come together, because that's the ultimate goal, of course, that we want to discover something that extends our understanding beyond the standard model. Well, we are not there yet, but I'm going to outline a few ways in which this could happen. And then in Matteo's talk after mine, he will outline some other possibilities. And the rest of the day, of course, is also about BSM searches. So that's the question. How can high precision neutrino experiments constrain physics beyond the standard model? I've ordered my talk according to dimensionality. I'm going to start with the dimension 4 operator that couples neutrinos to a dark sector called the Neutrino Portal. Then I'm going to talk about neutrino magnetic moments, and at higher dimensionality about effective field theories for new physics in the neutrino sector more generally. So the Neutrino Portal is basically this operator. There is the charged lepton, the lepton doublets from the standard model. There's the standard model Higgs, and here there is the possibility to couple to a singlet fermion, more commonly known as a sterile neutrino. That's the only renormalizable operator through which the standard model can couple to a singlet fermion. And that's why this is rather important, and that's why it's receiving so much attention. What it does is, well, it leads to mass mixing between the standard model neutrinos and this sterile neutrino, and thereby it can lead to the direct production of these sterile states, or if they're light enough, to oscillations. So oscillations, of course, immediately bring us to the short baseline anomalies. I'm going to quickly walk you through the anomalies, especially those that Carsten has not covered yet. So the reactor anomaly, you've seen this. There is this or let's say there was this deficit of the observed reactor neutrino fluxes compared to the predicted ones. But my take on this is that there has been this recently updated measurement of the beta spectra from uranium-235 fission from the Kurchatov Institute. And with that, the data and the prediction move much closer together. So once again, this is the old pre-2021 plot, and this is now the post-2021 plot. And so I would say that with this new measurement, that basically redoes some of the things that were done at ILL in the 1980s. My take on this is that the reactor flux anomaly is has been resolved. But it's not the only anomaly. You've seen the spectral wiggles that several experiments have seen. This is another version of the plot that Carsten showed. This one is by Jeff Berryman and Patrick Huber. You see here once again the neutrino 4 result that appears to strongly favor oscillations. And then from all other reactor experiments, you get closed regions at low significance, and then at higher significance, you get a rather non-trivial exclusion limit. So that one, I would say the jury is still out on, so that one's still unresolved. Same goes for the gallium anomaly. This is before BEST what it looked like. So there were the GALEX and SAGE measurements that were all substantially below the predicted fluxes indicated here by this dashed line. And now with BEST coming along, the major novel thing that BEST adds is that it consists of two independent detection volumes. The hope was, of course, that the different deficit would be observed in the two volumes, which could be a first hint for oscillations. But in fact, the deficit in both volumes is the same. So one question here is, I would say the source here is probably well understood, as we also discussed after Carsten's talk. In particular, the measurement of the intensity of these sources is a calorimetric measurement. So if something goes wrong with a calorimetric measurement, you typically lose energy, which means you would underestimate the power of the source, which means you would see an even larger deficit. And since that's not so, this would, if there wasn't a systematic uncertainty there, this could only make the anomaly even larger. So I consider that unlikely. Of course, there is this thing about the radiochemical method for extracting the produced germanium nuclei from the gallium tank. It is a radiochemical experiment after all. And there's always a chance that one way or another, some of the produced germanium nuclei are missed, which means we would effectively miss neutrino interaction. That is a systematics that's kind of common to all these gallium experiments. Therefore, I think it would be really great to have such an experiment done with a different method. So in that sense, I'm very, very disappointed that SOX, for instance, did not materialize. The idea of putting an intense radioactive source underneath the Borexino detector. That would probably have gone a long way in resolving this. However, one should say, yeah, it is a radiochemical method, but on the other hand, that radiochemical method has also been applied quite successfully to measurements of solar neutrinos that agreed with other measurements of solar neutrinos. So in that sense, solar neutrinos cross-calibrate this method. So, well, the jury is still out on this one too. Now let's come to accelerator-based experiments. This is the infamous LSND setup. There was a beam stop here where lots of pions were produced. It was a thick target, so the pions were stopped. They decayed at rest, and the neutrinos from pion decay at rest were then observed in this detector that was located about 30 meters downstream of the target. You also know the result. There's a significant excess of the data in black over the background predictions in green and red, and that can be well fit by oscillations as shown here in blue. Once again, no explanation for LSND has been found so far. And one of the reasons it's so hard to find one is LSND uses inverse beta decay as a detection signature, and they tag the neutron. So in order to fake that signature, you need an electromagnetic signal followed by the delayed coincidence of a neutron capture. And that's pretty hard to fake. Now, mini-boon, of course, was meant to test LSND. I don't need to walk you through these plots. But mini-boon, for all practical purposes, I would say, is also unresolved. We have more information now thanks to microboon. So this is the result, or some of the results that microboon showed last year. Microboon has explicitly tested the new E appearance hypothesis. And if there was new E appearance at the level observed by mini-boon, then these 4 different microboon samples should have aligned more or less with the red lines here. They did not. They are here, the data points, and the gray bands are the standard model prediction. So that at least disfavors new E appearance. It doesn't completely rule it out, as shown in this plot here. So this is on the horizontal axis, the effective mixing angle for mu to E oscillations at short baseline. The vertical axis is delta M square. The bluish region here in the background, that is the mini-boon region. And the blue and orange curves here are from 2 different microboon analyses. So you see they disfavor a significant fraction of the mini-boon allowed region, but they're not completely ruling it out yet. One should also say that much of the sensitivity that we find here is driven by the fact that microboon in fact observed downward fluctuations. So this gives them a little bit of an edge. This means that the observed limits here are slightly better than the expected limits. Putting everything except microboon, I should say, together in a global fit, we see that even though sterile neutrinos could perhaps still explain mini-boon and LSND, they are pretty firmly ruled out when other experiments are taken into account. So what's shown here is the mixing between the hypothetical sterile neutrino and muon neutrinos. If you want mu to E oscillations mediated by a sterile neutrino, the sterile neutrino has to mix with both electron neutrinos and muon neutrinos. So here we are focusing on that mixing with neutrinos. If the anomalies are taken at face value, then they would put us into one of these red regions here. If we, however, look directly at data on new moon disappearance, then we are forced to be to the left of this black curve here. So there's pretty severe tension here. That tension can be quantified. The p-value is less than 10 to the minus 4. So that's a pretty firm exclusion of this simplest sterile neutrino model. So what do we do about this? Of course, we need to further scrutinize the anomalies, and that program is in full swing, for instance, with the Fermi-Lab-Schwarz baseline neutrino program. Perhaps at some point, it's also good to scrutinize the null results, especially the older ones. However, I should say that even if you remove entirely a single null result from the plot on the previous slide, that does not fully resolve the tension. You need to take out at least two of them. For instance, if for some reason you take out Minos and IceCube, yeah, then you can do something. But we have no reason whatsoever to believe that Minos and IceCube limits are not robust. Now, from the theory side, of course, it's always interesting to consider extended models. And I'm not going to say much about this because this will be a central theme of Matteo's talk just after mine. So extended sterile neutrino scenarios, where the sterile neutrinos not necessarily oscillate, but their decays can do interesting things. And there are some quite promising scenarios in this context, but I leave that to Matteo's. Okay, so to conclude with this first part of my talk, there's lots of unanswered questions in this field, but I think that's a good thing because if there weren't any unanswered questions, we'd be out of work. And then the good thing is that there's realistic hope that upcoming experiments such as the Fermi-Lab-Schwarz baseline program may at least help us resolve some of these anomalies. And even apart from that, all this research that's going into resolving the anomalies, I think whatever the outcome is going to be, whether there's going to be new physics or not, it'll teach us important lessons for the future, right? For instance, if there's something wrong with the way we understand neutrino interactions in a detector like Mini-Boon, then we'd better want to know about it, because perhaps the same misunderstanding could also affect future experiments like Dune and Hyperkamiokande. Okay, so much about sterile neutrinos from my side. Let's switch gears entirely and look at higher dimensional operators that contribute to new physics in the neutrino sector. And perhaps the simplest such operator is a neutrino magnetic moment. Now, what's a magnetic moment? From a theorist's point of view, a magnetic moment is this term in a Lagrangian. There is a coupling to the electromagnetic field strength tensor. There is a tensor current of neutrinos. So nu L, these are the standard model left-handed neutrinos. Sigma mu nu is the commutator of two gamma matrices. And in order to make this whole thing Lorentz invariant, the neutrino field here on the right-hand side has to be a right-handed neutrino field. That means for Dirac neutrinos, well, it's just a right-handed neutrino. For Majorana neutrinos, it's the charge conjugate of a left-handed neutrino. But a magnetic moment operator, importantly, is always something that couples left-handed to right-handed. Well, and there's, of course, a coupling constant up front. That's what we call the magnetic moment. And because that's a dimension 5 operator, that coupling constant here has mass dimension -1. Now, that operator, in fact, is generated even in the standard model at the one loop level. Here are the relevant loops. A neutrino goes to a charged lepton and a W, and then you can attach a photon to either the W or to the charged lepton. So that exists in the standard model, but it's tiny. The numerical value is that the neutrino magnetic moment is order 10 to the -19 Bohr magnetons. So Bohr magnetons, that's the magnetic moment of an electron, essentially. And the reason it is so tiny is because it requires a coupling between left-handed and right-handed neutrinos. Now there's a W in this loop, and the W couples only to left-handed neutrinos. So this means if you want to get a right-handed neutrino here on one of the external legs, you need to include a spin flip, meaning a mass insertion, on one of the external legs. Well, and that costs you a factor of the neutrino mass. And that's what makes it so tiny, because it's suppressed by the neutrino masses. In addition, of course, it's also suppressed by the W mass. Now, but when an effect is tiny in the standard model, that's good news, because that makes it much easier to see new physics. And that's why magnetic moments are a good way to look for new physics. In the most general case, I'm going to call the right-handed neutrino now again a sterile neutrino or a general singlet. I'm agnostic for the moment about whether that has anything to do with neutrino mass generation and so on. Let's just assume there is a singlet field, then this is one way of coupling to it. This can be achieved in concrete models. Here's an example. So here you see a diagram, for instance, in a model that involves quarks and leptoquarks in a loop. And that's in fact a model that was motivated by some of the flavor anomalies. So that's why it's interesting, because there's this interesting connection there between quark flavor anomalies and neutrino flavor. But this is just to show you how this can be generated by, for instance, TeV scale new physics. So nothing too extraordinary. Now, how do we look for this? There's many ways of looking for it. And one interesting way of looking for it is by using solar neutrinos, but not in solar neutrino detectors, but actually in dark matter direct detection experiments. Solar neutrinos are always present in those experiments. In fact, they make up the famous neutrino floor. So these yellow regions down here, beyond which dark matter searches will suffer from an irreducible neutrino background. Here's what this neutrino floor looks like. The horizontal axis here is the electron recoil energy that you get when a neutrino scatters off an electron, and the vertical axis is the event rate. Now, in the standard model, the neutrino floor looks like this black dotted curves here. The upper one is for all flavors, the lower one is only for mu flavor. You see there's all these steps here, which are just reflections of the structure in the solar neutrino spectrum. Here at the lowest energies, you're dominated by the PP neutrinos, and it's basically the differential event rate is basically flat. I've also put some data on this plot. There's Borexino here. Borexino has, for this purpose, a relatively high energy threshold. So it sits here in the region where the spectrum is already falling off. Whereas dark matter detectors like here, xenon 1 ton, well, they reach much, much lower energy thresholds. So they really probe PP neutrinos here. Now, what happens if you switch on a magnetic moment? That's shown, for instance, by the blue curve. If the neutrinos have a magnetic moment close to the current upper limit, then this rate will be substantially enhanced at low recoil energies, while being more or less consistent with the standard model at high recoil energies. That can be easily understood, because if there's a magnetic moment, then neutrinos can scatter on electrons by exchanging a photon. And a photon is massless, meaning the lower the momentum transfer in this propagator here, the larger the event rate. So that explains why there is this significant increase by several orders of magnitude here as you go to lower and lower recoil energies. I've also put a second curve here, which is for right-handed neutrinos with a non-negligible mass. In that case, the kinematics is different, and basically all these features in the solar neutrino spectrum get shifted around. So there's lots of highly non-trivial features here that one can look for. And this can be done. Here is a first set of exclusion limits on neutrino magnetic moments. The horizontal axis is the mass of the right-handed neutrino, which is like the one new particle we need in this scenario. And the vertical axis is the magnetic moment. I'm not going to walk you through all of them here, but let's just focus here on xenon 1 ton. The dashed curve here is the xenon 1 ton exclusion limit. And if you take this small excess that xenon 1 ton has observed last year, if you take that at face value, then you end up in the purple region here. There's also limits from other terrestrial experiments, but these are usually relatively weak compared to what you can do with a dark matter detector. Now, these are not the only limits. I'm not going to go in detail to all the other limits, but let me just mention that there are very, very strong limits here for light sterile neutrino masses from stellar cooling, where the idea is that through the magnetic moment operator, you'd produce lots of right-handed neutrinos in stars. And the right-handed neutrinos, because they are not stopped by anything, they will leave the star and carry away substantial amounts of energy. And then stellar evolution would be completely different from what it is. For instance, the sun would already have used up all of its fuel by now. And this can be used to set extremely tight limits here. There's also a limit from supernovae based on the same physics. I'm showing that as a blue dashed curve here, because there was a recent paper basically calling this constraint into question. But if you take it at face value, then you see that it really disfavors a huge chunk of parameter space here. There's also cosmological limits. I'm not going to tell you in detail how these are derived, but we can do this later in the discussion. I'm just going to put them on the plot and show you that here from BBN and the ineffective measurement in CMB, we again exclude large chunks of this parameter space. There's a lot of interesting physics going on here that I'm happy to discuss, but I'm going to leave that to the discussion session. So the conclusion from this part of my talk is, yeah, magnetic moments are an interesting way of looking for new physics. There are already some very tight constraints, but also especially with the advent of new dark matter detectors, there is a chance of learning more. And what's interesting is that the parameter region that is being probed at the moment here around magnetic moments of maybe order 10 to the minus 11 Bohr magnetons, that's exactly where TeV scale new physics would put you. So for instance, this leptoquark model here that's been motivated by the B physics anomalies, that would put you somewhere in this region here. So we are really probing an interesting region of parameter space here. And notice also that that's exactly the region where cosmology is relatively weak in limiting this. So conclusion from the second part of my talk, neutrino magnetic moments are interesting, and as for the future, there are more ways in constraining them that I am also happy to discuss, but have not yet put into the talk. Namely, there's also an interesting impact on supernova neutrinos and high energy astrophysical neutrinos, which has not yet been used to set constraints, but which in my opinion could also be quite interesting. Okay, now in the last few minutes, let me talk about a more general EFT approach to new physics in the neutrino sector. Well, EFTs, that's usually what the theory community does when they have no strong leads for any particular new physics model. So we try to be as agnostic as possible and just assume that the new physics is relatively heavy. That's being done with great success in collider physics or flavor physics, but it can be done also in neutrino physics. What this means is, up to a certain dimension, in this case dimension 6, you basically write down all possible interactions that you can put in your Lagrangian based on its symmetries. And then you try to constrain the coefficients of all of these operators. And by doing that, you effectively constrain large classes of new physics models living at high mass scales that would, when integrated out, generate these effective operators. Now, here's what some of the most important operators in neutrino physics look like. The way they are typically parameterized is in terms of the Fermi constant multiplied by some parameter called epsilon. So this just means we are writing the strength of this operator relative to standard model weak interactions. So GF is the Fermi constant that gives the strength of standard model weak interactions, and we multiply it here by a free parameter that tells us how strong the new physics is compared to standard model weak interactions. There's two main classes of these operators that affect neutrino physics. The upper one here, these are neutral current operators, which couple a neutrino current to a quark or lepton current. But remember, you see here the neutrino stays a neutrino here. The other possibility is charged current operators shown down here, where we have a neutrino lepton charged current coupled to a charged current of quarks or fermions. So these neutral current operators, those, well, obviously they affect neutral current neutrino scattering, but more importantly, they affect neutrino matter effects, so coherent forward scattering of neutrinos on the material they are propagating through. So this is mostly something that affects the propagation of neutrinos. The charged current effects, on the other hand, they affect neutrino production and detection, because most neutrino production and detection reactions are, after all, charged current reactions, and those would be modified if these operators exist. Notice also that we put a lot of indices on the coefficients here, and that's because we want to be agnostic about the flavor structure of the new physics. That's in particular because when the new physics is flavor violating, it's usually much easier to see than when its flavor structure is aligned with the standard model. In other words, for instance, when you have a nuclear decay and you have flavor conserving new physics, well, then what the new physics does, it modifies your nuclear decay rate by a tiny amount that you probably cannot see because you have a large uncertainty on your nuclear matrix element. Whereas if the new physics is flavor changing, so if a nuclear decay should suddenly start producing, say, mu neutrinos, then this is something that you may be able to see more easily. Okay, now there's a large program going on both on the experimental side and on the theory side to constrain these operators. Here's a set of plots from a recent paper from the Spanish, from the Madrid group. Yeah. And I don't want you to look into these plots in all too much detail, but I want you to only look at the scale of the horizontal axis. So all of these plots show the value of one of these coefficients versus delta chi square. And you see that here on the horizontal axis, there's order 1 numbers. And this means we are not all too sensitive to these couplings yet, at least for most flavor structures. So in other words, we are sensitive only to interactions that are not too different in strength to standard model weak interactions. Now, the other possibility is new physics that leads to novel charged currents. And while we can, of course, look for those also in the conventional neutrino experiments, there's an interesting new player in the field, and these are collider neutrinos. One of these experiments is already more or less exists, and that's the Phaser Nu experiment at the LHC. Here's a sketch of what it looks like. Imagine the LHC tunnel and look at the Atlas interaction point. So that's where the beams collide to produce whatever Atlas is looking for. Now, in these proton-proton collisions, of course, a huge flux of mesons is being produced, most of them going straight down the beam pipe. So they are uninteresting and unobservable to an experiment like Atlas. However, these mesons will eventually decay, and when they decay, they produce neutrinos. So there's a large number of neutrinos going down the beam pipe. Now, the LHC is a circular collider, so the beam pipe eventually curves away. And what Phaser Nu does is, it is located in a straight line down from the Atlas interaction point at a distance of something like 500 something meters, I believe, and it's looking for those neutrinos. That's quite peculiar, first, because there are a lot of these neutrinos, and second, because they are very, very high energy. So this is the highest energy terrestrial neutrino source that we have. These are neutrinos with up to TeV energies, right? So much higher than what we see in dedicated terrestrial neutrino experiments. Well, and then the detector itself, it sits in some side tunnel that used to be a transfer line during lab times and is currently unused. There is going to be, at the very first stage, there's going to be a neutrino detector that's based on the nuclear emulsions that were developed for the OPERA experiment. And this is followed by a spectrometer and a calorimeter. This, of course, is not only good for doing neutrino physics, this is also good for searching for all other kinds of light new physics. And there are a number of people in the audience here who know much more about this physics program than I do. I mean, I encourage you to talk to them, of course. But here, let's focus on what Phaser Nu can do for neutrino physics. So the idea is measure the neutrino fluxes from the LHC and compare them to predictions and see if anything is amiss. The great thing is, because these are so high energy neutrinos, we can see all neutrino flavors. So we can see tau, mu, and e neutrinos. And here's a plot that shows the expected constraints on some of these operators. I'm only showing those here where Phaser Nu is at least competitive with other constraints, but I can also show you a plot that does this for all possible flavor structures. So the indices you see on these operators here, the upper indices are the quarks appearing in the operator. The lower indices are the neutrino and charged lepton flavors appearing in the index in the operator. And the index P or R here, or T, that tells you something about the Lorentz structure of the operator. So P means a pseudoscalar coupling, for instance, mediated by a new pseudoscalar particle, like from maybe an axion-like particle or so. R stands for right-handed currents, which is what you get, well, you get it, for instance, from left-right symmetric models. And T is a tensor current, which are usually quite hard to get from a theorist's point of view. So what you see here is on the horizontal axis, we express the sensitivity of phasor nu in terms of these epsilon. So 1 means an interaction as strong as the standard model weak interactions. 10 to the minus 2 means an interaction that's 100 times weaker than standard model weak interactions. On the bottom horizontal axis, we translate this into sensitivity to a new physics scale. So here is TeV scale new physics, and there's 10 TeV scale new physics. So first of all, what you see is that many of these bands here extend towards a TeV and into regions of couplings much weaker than standard model weak interactions. So that's already good news. What's perhaps even more interesting is if you compare to these black arrows here that show external constraints on these operators, for instance, from meson decays. I find it quite astonishing that for some of these operators, phasor nu can be competitive with meson decay experiments, even though phasor nu, quote, quote, only has neutrinos at its disposal, but it really has a lot of neutrinos, and because they are high energy, they are relatively easy to detect because their cross-sections, their interaction cross-sections are fairly large. And remember that phasor nu, this is just, I mean, phasor nu was basically built from recycled parts of other experiments. There's really a very cheap initial stage experiment. So I see great potential for upgrades here. There's, for instance, a proposal of a so-called forward physics facility at the LHC, which would see this program taken to a much higher level. So what's the future here? Oops. This SMEFT formalism, I've shown it to you here for phasor nu, but of course this can also be extended to lower energies. And we are currently working on basically developing a unified framework that consistently couples the effective field theories in the deep inelastic regime, in the quasi-elastic regime, and in the resonance regime in one transparent tool. Okay. So, and that also brings me to the summary of my talk, which is basically all the bullet points that I already showed you during my talk. There's lots of interesting ways in which new physics can show up in the neutrino sector. I only gave you a very brief subset of those. But on all of these fronts, we can expect significant progress in the next couple of years. So I'd like to thank you for your attention and leave you with the pictures of the junior collaborators with whom I worked on some of the material that I showed you here. Thanks a lot.
Thanks so much. Yeah, we have some questions.
Yeah, I have a question about the neutrino magnetic moment.
Yeah.
Can you bring back that plot for the
that one?
For example, yeah.
Yeah.
What I'm confused about is the Borexino line. I would say is about 7 or 8 times 10 to the minus 11.
Mm-hmm.
And from their 2017 paper, they claim it should be 3 times 10 to the minus 11.
Yeah, that's because here we have assumed that the magnetic moments affect only muon neutrinos. I think Borexino have assumed flavor universal couplings.
Ah, I see. Is there any reason to suspect why it should only...
No, that was basically an arbitrary choice we made for this plot.
I see. Okay.
Yeah.
But does that improve the physics reach of? I mean, you mentioned that sort of 10 to the minus 11 is sort of the most interesting region.
Yeah, I mean, it makes it improves things by an order 1 factor if you assume flavor universal couplings.
I also have a question on the magnetic moment.
Yeah.
So when you induce a magnetic moment,
mm-hmm.
typically the theory would also induce a neutrino mass.
Excellent point. Yes, of course.
So at the level of 10 to the minus 11 Bohr magneton, it seems to me that the constraint from neutrino mass would be significant.
Yeah, so that's a point that I skipped over. I might have backup slides on this, but I can. Well, the main point can be seen already from these diagrams here. Basically, whenever you have a diagram that generates neutrino mass, that generates a neutrino magnetic moment, when you remove the photon line, that's effectively a contribution to the neutrino mass. And so there's a close connection between the neutrino magnetic moment and the neutrino mass. And indeed, in the vanilla models of this type, you typically, if you have an observable neutrino magnetic moment, then you predict neutrino masses that are several orders of magnitude higher than what we know the neutrino masses to be. So there either needs to be fine-tuning between this contribution and another contribution to the neutrino masses, or you can play some games with extra symmetries. For instance, in this model from which I showed one diagram here, we've introduced the so-called Voloshin mechanism, which introduces it basically puts two different leptoquarks into multiplets of a new global SU2 that is broken only at the loop level. And with that, we can achieve a situation where the contribution to the neutrino mass vanishes at 3 level, but the one to the magnetic, or at lowest order, and the one to the magnetic moment does not. So that's what we have done here. But yeah, I maybe this was a bit misleading when I said that this is generic, that TeV scale new physics generates magnetic moments at this level. Well, it does, but it also generates neutrino masses. So there has to be some mechanism at work that suppresses that.
Thank you. So these models also would predict some charged particles below a TeV scale. Is that correct?
Well, at the TeV scale. So these leptoquarks here, they live at the TeV scale. I don't remember the exact number. I think it was maybe, I don't remember the exact number. It was order TeV.
Thanks.
Magnetic moments are popular, so I also have. Well, given that there are these astrophysical limits from red giant cooling, also there is another limit from existence of Cepheid variable stars, which are all about 10 to the minus 12 for magneton. It seems that the dark matter experiments cannot quite make it down to that level, right? Did I misunderstand you?
No, that's a fair point, but they have a higher reach in the mass.
Right.
So basically the astrophysical constraints, they are limited by how hot the objects are.
Exactly.
So this is basically driven here by red giant stars, and there are the supernovae. Yeah, and the dark matter experiments have the advantage they go to slightly higher masses for the right-handed neutrinos, but they can't go quite as far down in magnetic moment.
Right. So my question is, given that those limits are all 10 to the minus 12 for magneton, can you imagine that there could be beyond the standard model physics, which would not be applicable in red giant cooling or other astrophysical cases, which may push the magnetic moment up that high?
I've spent some time thinking about this because, yeah, these limits are always a headache when you will want to build new physics models.
Exactly.
And it's very, very hard. So people have, for instance, proposed these chameleon models where particle properties are different in matter than outside matter. But that's pretty much the only scenario I'm aware of that circumvents these limits. And I would consider this already not impossible, but I would consider it relatively exotic. Not uninteresting, but relatively exotic.
Thanks.
Hi, I have a question about the LSND.
Yeah.
You mentioned at the beginning that, okay, there is an oscillation, and there are actually, you have the measurement of antineutrinos, where you expect the enhancement, but also they have a flux of neutrinos. And what happened with that? Do they observe also an oscillation? Because that should be the prediction.
I think in neutrinos, they have much less sensitivity. First of all, remember this is an appearance measurement. Now, in antineutrinos, their primary flux contains muon antineutrinos, but almost no electron antineutrinos. There are a few from decay in flight, but to lowest order, no electron antineutrinos. Whereas in the neutrino sector, there's a large flux of both muon neutrinos and electron neutrinos. That makes it much harder to do an appearance measurement. And second, in neutrino mode, you don't have inverse beta decay as a detection reaction. And inverse beta decay is really great because it has this delayed coincidence signature. So that makes background suppression much, much easier in antineutrino mode than in neutrino mode.
Okay.
They do have a measurement. So there's a scattering process of electron neutrinos on carbon-12. So they have a measurement of electron neutrino disappearance from that data.
Other questions? Yeah.
Thanks, Joachim. Two quick questions. So the first one, the supernova bound here, could you explain why it may not apply?
Okay, so I would say, to be honest, this is not generally accepted wisdom in the community. So I think most people still think the supernova neutrino bound is relatively robust, and probably most people are right. But there is an interesting dent in this notion due to a paper by Kfir Bloom from 3 years ago. So what they call into question is whether the neutrinos that we have observed from supernova 1987A are actually from a cooling neutron star. What they propose as an alternative is that the neutron star is accreting material and that the neutrinos are emitted by that accretion disk. And that would decouple the neutrino emission from the cooling of the neutron star. So in that case, the duration of the neutrino burst would no longer tell you anything about how fast the neutron star is cooling, but rather it would tell you something about how material is being accreted onto the neutron star. And therefore, you'll have much more room for new physics now, because you let the neutron star be cold. You wouldn't see it in the neutrino signal if the neutrino signal was coming from an accretion disk rather than from the cooling neutron star.
So in that case, you would still produce a lot of these states, right? Independently of
yeah, you would still make
that.
them, and the neutron star would cool very, very rapidly. But the notion there is you wouldn't be able to see it because you still get neutrinos from other sources. And so the duration of your neutrino burst would be unaffected.
I wonder if searches for accompanying photons coming from these decays could help here. Because the flux of these new particles would be huge.
But remember, at the time that this happens, that's the very early stages of the explosion. So the outer layers of the star probably haven't even realized yet that there's an explosion going on. So those photons would have a difficult time getting out.
I see.
Can I just say that could I just say that there are those of us that are queasy about any kind of supernova limits, cooling limits especially. I mean, I'm not saying that you can't get them. Because clearly, if you shorten the duration of the neutrino pulse that was observed in IMB and et cetera, 2 months and CAM2, you shorten that enough, it conflicts with the data we have. But we don't have much data.
Yeah.
And just keep in mind that the energy in the supernova explosion is only 1% of the energy that's resident in the neutrino fields in the star. So that disparity in energy just makes me a little queasy about, constraints from supernovae. Anyway.
Yeah, thanks for that comment.
And
so just adding fuel to your fire.
So the other question was regarding the EFT approach.
Yeah.
Are the bounds better than the reach of LHC limits on potential mediators of these operators, or are we not quite there yet?
So typically the LHC reach for new charged particles does not reach a TeV, right? I'm not sure how this will be for the high-Lumi LHC. But at the moment, new charged particles that are not color charged but only carry electroweak charges are somewhere in the few hundred GeV range. And that is, if you look at this propaganda plot here, it seems that those limits may have a somewhat higher reach in mass. But of course, what you have to consider is also the flavor physics limits here. They may become better over time. But then again, also, as I said, Phaser Nu is still a very small, early stage experiment. There's certainly room to do something more sophisticated there as well.
Thank you.
All right, let me suggest we continue our questions over coffee, and thank Joachim again.
Thank you all.